Some problems involve addition of force vectors that lie in a two-dimensional space, such as the xy plane. These forces are referred to as coplanar forces. Remember, coplanar means within the same plane, just like collinear means along the same line. To use the component method, it is necessary to be able to resolve a vector into its rectangular components, i.e. its x, y, and z components. These are known as the rectangular components of a vector. The term resolving a vector implies separating the vector into its x, y, and z components, such that when these vector components are summed, the result is the vector itself. For a two-dimensional vector in the xy plane, such as vector f in blue shown here, we need to determine its x component and y component, noting that its z component is 0 because this is a two-dimensional space. F is in the xy plane. Here, the scalar magnitudes of the rectangular components of force F are determined using vector addition, such that vector F equals vector fx plus vector fy, or f sub x plus f sub y. So we know from things we've already learned in chapter 2 that if we add the fx vector to the fy vector, we obtain the f vector in blue. So notice we're creating, again, a parallelogram inside of which are two triangles, specifically right triangles. And this angle, let's say, is a known angle theta. So because the components form a right triangle, they can be determined from trigonometry. So looking at this right triangle and recalling principles of trigonometry, we can set up sine and cosine of theta, where sine theta, as you recall, would be the opposite side over the hypotenuse, and cosine of theta is the adjacent side over the hypotenuse. Therefore, sine theta equals the magnitude f sub y over the magnitude of f. Because sine theta is here, the opposite side is this side, which represents f sub y, and the hypotenuse is the blue vector, its magnitude, which is f. Cosine theta is the adjacent side, f sub x, this side here, adjacent to theta, over the hypotenuse f. So rearranging, we see that f sub x equals f cosine theta and f sub y equals f sine theta. So if we know the magnitude f and we know theta, we can quickly solve for fx and fy. So in this two-dimensional space, we have the positive x direction defined as to the right and the positive y direction defined as upward, which is why we label x here and y there. So by inspection, the x component of this vector is positive and the y component of this vector is also positive. Sometimes the direction of a vector is defined using a small slope triangle instead of an angle. So here is that type of example. So whereas this force vector was in the first quadrant of the xy plane, this force vector is in the fourth quadrant, right? Because we have quadrant 1, quadrant 2, quadrant 3, and quadrant 4. So here, this force vector is directed in this manner. And again, it has its own x and y, or rectangular components. Now notice there's no angle, no theta here that's given. Instead, we have this slope triangle, where this line here is parallel to the y-axis, and this line here is parallel to the x-axis. Lowercase a, b, and c would be numbers, integers, and common values of a, b, and c would be 3, 4, 5, and 5, 12, 13, which refer to the lengths of sides of a right triangle in which all the sides have lengths that are integer values. So using similar or proportional triangles, we have the following. So for instance, A over C, if we do the ratio A to C, which is this length over that length, that equals F sub X over F, because F sub X is this horizontal piece of the vector F, and A is also horizontal. C is the hypotenuse of the slope triangle, and vector F has a magnitude F that's the hypotenuse of this gray triangle. So the small slope triangle and the shaded gray triangle are proportional or similar triangles. So the ratios of the corresponding sides of these two triangles are equal. So again, A over C is F sub X over F, and similarly B over C is F sub Y over F, because B is the vertical piece of this triangle and F sub Y is the vertical piece of this larger triangle. So rearranging, we have F sub X equals A over CF and F sub Y equals negative B over CF. Now this is very important to realize that we did insert a negative here. Here we're really just referring to the absolute values, absolute magnitudes, but here we're actually making sure to indicate whether the vector goes up or down in the positive or negative y direction. So we did insert this negative here because by inspection, the x component of this vector is positive, but the y component is negative. Okay, so that's the two different ways that we could specify the direction of a vector in this two-dimensional space, using either an angle that's measured with respect to one of these axes or using a slope triangle. It's also a good idea to go ahead and mention that these equations, f sub x equals f cosine theta and f sub y equals f sine theta, will not be the same if theta is, instead of this angle, theta is this angle here. Okay, the sine and the cosine will be swapped if instead of calling this angle theta, we call this angle theta. Okay, so it's very important to really study the diagram that you are given to make sure that you're using the trigonometric identities in the proper way.